Next talk will be given by Dr. Eli Osherovich, the head of self-driving cars labs in Yandex Israel. Dr. Eli leads the Yandex SDC centers in Israel, driving the next revolution in mobility. Together with vast industrial experience, Eli brings his special expertise in building large-scale AI-centric systems. Prior to joining Yandex SDC, Eli was one of the founders of Amazon R&D Center in Haifa, where he led multiple projects of Amazon Go, world's first cashless store.
Can you hear me? Oh no. Okay. So apologies for the technical troubles. My name is Eli Osherovich. I lead the Yandex self-driving cars in Israel. And actually, a full disclaimer, I'm not an expert in AV, autonomous vehicles. Started this position about 3 months ago, so I learned the field. I'm coming from deep learning in image processing and things like this. The whole field of self-driving cars is new to me, and personally, I'm very excited. So I came here to kind of share my excitement with you. Okay? Well, let's start with the car. Do you remember when the first car was invented? Anyone? Well, this is 1885. Benz actually invented what we today consider as the first, let's say, modern car. And it made a long way till 2000-something. Here I gave you a previous example because we use these cars for our, retrofitted models to test and, develop the self-driving system. So are these two cars similar or identical or close one to the other? They look different. They look different, but actually inside they are pretty much the same. So essentially the car didn't change that much. Okay, and the question is, if this is a typical example of, let's say, a technological progress, what do you think? I think no. We know other technologies that during the same time period made a much, bigger step forward, a much bigger step. Okay? And of course, computers are a good example of such a technology. If you take a mechanical computer from about the same year, compare it with something that we have today, it's a tremendous difference. Okay? Not anywhere close to the cars that we saw before. Okay, but the car, on the other hand, gives us a very comfortable seat, a very reliable mechanical platform. So we can take the best of the both worlds and combine them together into a very smart car, the one that can actually drive by itself without a human intervention, without a driver, without anyone, sitting there and steering the wheel. Okay, and how do we do this? Well, there are many approaches, but basically all of them start with the sensors. There are many companies doing the self-driving cars, but I think every one of them actually use some kind of sensors. Tesla are bidding on cameras, Yandex, Waymo, and many more are using cameras and LiDARs. We'll see this in the next slides. So how do we do this? In the first stage, we would like to know where the car is. So we call this the localization problem. Once we know our location, we would like to know what we see around us. This is the perception problem. With the perception, we know there are more cars, pedestrians, cyclists, you name it, animals, whatever, around us, and we should know what they are going to do in the next step, in the next second or 5 seconds or something like this. We must predict their behavior, right? So we use prediction block. Once we know the position and probably speed of every object that we detected previously, we would like to plan our own motion to be able to not, bump into anyone and to obey all the rules that we have on the road. So we have the planning block, and finally, once we have the trajectories that we would like to execute, we kind of translate this into commands that the machine can understand, this is the control block. Okay? Is this the only possible approach? Definitely no. But many, many companies are using this kind of pipeline to develop their self-driving cars. The other approach I will show on the next slide, but due to the time limitation, I'm going to cover these two in this lecture, and the rest will be covered in the next lecture. Okay, so what is the other possible approach? This is some kind of end-to-end learning. We have the sensors, we know the commands. So one would like to build a supernet that takes the sensor data, the cameras, the lidars, the radars, whatever you are using on your camera, on your car, and translate it directly into command that you send to your steering wheel, to your brakes, accelerator, etc. This one is a very holistic approach, a very interesting, and this one has many, potential benefits, like being able to teach your car, you just have to drive it. If you drive it sufficiently well for a long time period, it will learn to do the same. Okay, so you don't have to, say, hey, this is another car, this is a pedestrian. You don't have to label your data. You don't have to do anything else. It's a kind of unsupervised learning at its best. Okay, and by the way, if you think that you can develop such a net, or you would be eager to develop or work on this problem, we should talk. Okay, so before we go back to our algorithmic blocks, let's take a pause and look at the sensors that we have in the car today. So this is a typical modern car with a bunch of sensors. Basically, people use radars, lidars, cameras, another kind of radars, and ultrasound sensors for the nearest, zone. What we are interested in is the kind of the range of the sensor, how far one can see with this kind of sensor, its robustness, if it works in, rain, snowfall, or things like this, fog, for example. And they have pros and cons in every different situation. Specifically in Yandex, we use lidars a lot. We use 3 lidars, giving us 360 constant, coverage. We use 6 cameras, again 360. We use radars, but I don't cover these in this lecture. So we are going to talk about the lidars and cameras. Lidars are actually used for 2 purposes. First is the localization problem. Okay, so remember, we would like to know where we are. So to this end, we use a bunch of sensors. This is global positioning, like GPS, Baidu, Galileo, you name it. We use IMUs and odometry. These are currently installed in all modern cars. But finally, we use our own in-house development, which is based on LiDAR data and high-density maps. Okay? And by the way, this last addition gives us fantastic precision of a single centimeter. Okay? This is a typical HD map. Okay? It does not look like a typical map, right? But what we have, in fact, is a highly, a very high precision 3-dimensional environment mapping. The other information that we embed into this map is kind of semantic information. We know where the lane is, if we can turn left or right from this crossroad, or where the traffic lights are. Using this, we can actually know where we are. We take the LiDAR data from the current frame, and we compare with this 3-dimensional map to know where we are. Once we find the match, we know exactly our position. And we know in this example that we can turn left because we have this information. Okay? Now we go to the next block, the perception block. Okay? In this case, we're using the LiDARs and the cameras together. And to do this most efficiently, our first step would be to align this data one against the other. So if you look at this image, this is the camera image with LiDAR data. LiDAR data is a set of points embedded onto it. If you look at this image, what do you think? Are these two aligned or not? So the key is to look at the lines. Okay, you see these horizontal lines, the vertical edges. They're very, very much aligned in this case. So this is an example of a good alignment. Otherwise, you will see the misalignment of these fine details. Okay, so if you use cameras and LiDARs, what do we do? In cameras, the 2D perception field, I would say it's a mature field. We have a bunch of excellent detectors, and some would even say this is a solved problem. Okay, is this the same in the three-dimensional field? Or anyone dealing with the point clouds or other three-dimensional structures? Yeah, just one. So what do you say? Exactly. Okay. So in the 3D world, it's a completely different story. Only 2017, I would say, some developments like this PointNet started to appear, and this is the, again, to the best of my knowledge, this is probably the first one that is using the three-dimensional data as is, because other approaches probably try to reduce it into 2 dimensions and then to apply the well-known detectors or something like this. So this one, on the other hand, uses the 3-dimensional points. And by the way, using points as is introduces a lot of challenges because, for example, points are not ordered. You cannot, count them. This is the first, the second, the third. So every possible permutation of a set of points should give you the same result. This is a huge challenge, by the way, if you think of it. But they actually solved it quite efficiently, I would say a very elegant way. This is just an illustration from the paper. Don't try to read it right now, but the idea is that we have a bunch of points. Each point actually undergoes the same transformation all the way to the very final layer where we do the full max over all the points. So we get this permutation in sensitivity or permutation. How to say it? So it's kind of, from this global feature, it's not sensitive to the permutation of the input point because we use the max pooling over all of them. Okay, the further development would be to use the 2D detectors together with 3D detectors. And this is exactly the continuation work from the same authors, the first on PointNet. Actually, they detect the objects in the 2D view and use this frustum to limit the search space in 3 dimensions. And actually here they added the bounding box over the objects because the first work actually provided us with the segmentation or classification, but not the localization. Well, the other smart approach is a VoxelNet. I have a very limited time, so I'm going fast. Again, this one also uses the 3D data as is, even though they use this tessellation into voxels. But still, every 3D point is processed as a 3D point. It's not a kind of a voxel attribute or something like this. We have a multi-view 3D, where the author actually combined the camera data, the front LiDAR data, and the top view LiDAR data to kind of produce 3 hypotheses for the object's locations and merge them all together. And actually, these are external developments. None of these was developed with Yandex or inside Yandex. They came from Stanford, Baidu, and Apple. Unfortunately, I cannot share the details of the internal implementation, but we use the ideas from these works. And actually, if we look at the Kitty data, which is quite outdated, we don't use this anymore. We actually got a pretty good results in terms of accuracy. So we are on par or even better in the hard cases. But what's most important in our case is the latency. Okay, because for the driving car, we must be able to recognize many, many times per second everything that happens around us. So these latencies are by far too big for a real-time application like ours. Okay, these were some kind of dry numbers. This is typical, This is a real screenshot from our demo. So we have a bunch of vehicles, a bus, car. By the way, we see the cars that are behind ours, which is not available for the human driver. So the system sees all around, 360 all the time in all the weather conditions, day and night. We see the pedestrians. These are little boxes of pedestrians. It's hard to see in this image. And this is actually all that I had today about the self-driving cars. And since the Yandex company is not known in Israel, a few words about it. So Yandex is most well known for its search engine. This is the #1 in Russia and #3 in the world search engine after Google and Baidu. But the self-driving cars is a different, subsidiary or a different company. We currently have 4 offices in 3 countries, and Tel Aviv being the latest addition. So I opened this office about 3 months ago, and we are, the first office that is actually a non-Russian or non-ex-USSR office of the company. We are looking for good people. This is not a secret. So if you are interested or as excited as I am in this field, you're welcome to chat with me or send your CV. Well, I think I will stop here. And thank you very much. If you have any questions, please feel free to chat with me. Have a good day.
Thank you very much for that nice talk. Any question from the audience? Everyone are very shy today. I will ask my own.
Sure.
For the perception model, when you move from one country to the other, do you need transfer learning
Yes,
for that? Yeah,
absolutely.
Okay. Can you
Absolutely.
talk about that a bit?
Yeah. This is one of the reasons why we have international offices. Here we have the cars as well as developers. So when we brought our car here from Russia to here, actually we discovered that the distribution over the vehicles is very different. So we have much more cyclists or bicycles or things like this. 2 wheels, all kinds of 2 wheels, single wheels that we have never probably seen. Different, not in these amounts in Moscow. So these were very different and challenging. The foliage is very different. The trees are looking very different. So sometimes we have false detections on the trees because of these, physical differences. But the most important difference is probably the behavior pattern. So being able to predict others might be a very different task from country to country.
Any more question?
Yeah, hi.
Hi.
My name is Roy. How you can handle a traffic change, like the government decide tomorrow to close the road or to put not entrance?
Well, this is an excellent question. So if you remember the holistic approach, when you just read your sensors and you conclude everything that you need to do, so you don't have a problem with this. You should be able to recognize this road is closed. You have some work done. Actually, we are using a mixed approach. We have lanes and roads and whatever else actually marked on the map. So we know this road is going to be closed. We mark it as closed on the map. But we might not know that in advance. Okay, so we do know to recognize obstacles. So we will be able to recognize that we cannot move on this road, because I assume it will be, blocked some way. So in the real time, we do know to recognize obstacles and to maneuver to pass along them.
Do you account for weather conditions?
Absolutely. Unfortunately, I don't have slides, but Russia is a kind of more problematic in that sense. They have a lot of snowfalls, rains, fogs. We have rains, but we are new here, so we didn't face it that much. But basically, snowfalls, heavy snowfalls. is a kind of challenge even for LiDAR, because they do return, the snowflakes can actually return your laser beams. Fogs are, a big challenge for cameras. Rain. Wind, no, we don't have any, particular problem with the wind unless it starts moving your cars in an unpredictable way. So it's I don't think our behavioral model will be able to cope with this. But this is the point. The more data, the more traffic patterns, the more the road conditions, road types you see, the better you drive. So we open centers in Israel, in the States, in Russia, differently, in Europe, things like this, to collect this data, to collect different conditions and all kinds of scenarios.
Will be the last question.
Hi. Do you have GPS data, inertial data, other data? You need it for the navigation, or do you actually, if I just put the car in how you want to develop it, and you just have the sensors for the people and stuff, do you still be able to drive? Or are you actually?
I'm not sure that I understood.
Do you need to know a map, and you need to know that there is a left lane, or are you able, let's say?
In our current approach, we do know where the turn is, and we actually conclude the lane. We know the lane position from our map and not from the real time. Even though we had these algorithms to detect lanes in real time, we currently don't use it because the map approach is much more robust, and it gives you a lot of benefits. Yeah. One of them is actually you compute. Being able to detect everything in real time demands, compute cost to be very, very high. So in a kind of, one of the reasons to offload it, basically knowing the lane a priori is kind of offloading this. This is the compute budget that you have on the car.
Thank you very much.
Okay, thank you.